introduction. Welcome to my talk. It's an honor to open this session. I will present a predictive analytical model for brittle failure in adhesive lab joints using the coupled criterion in the framework of finite structure mechanics. And that is applicable to the whole area of joints depicted here. And these predictive analytical models are still of high importance, especially in early design stages and optimization processes. And as you can see on the right, in the vertical cut through wine filter plate in engineering structures, typical different adhesive joint types are present, and all of them have to be assessed. And the problem is that at these material and geometrical discontinuities marked here with red circles, weak stress singularities are present. And the problem is that at these stress traces, near energy or strength criteria are directly applicable. And a framework that circumvents this problem is provided by finite fracture mechanics, assuming an instantaneous formation of finite-sized cracks. And in this framework, New York proposed in 2002 the coupled stress and energy criterion to predict onset if both criteria are fulfilled simultaneously. So for the analytical modeling approach, we require the stresses in the adhesive and the incremental energy quantities to predict crack onset. And for the former, a general sandwich type model proposed by the authors previously is used, which considers only the overlap region of these adhesive lab joints and a general loading. And it is a two-dimensional model assuming plate strain state and linear elastic material behavior for adherence and adhesive. The adherence are modeled using first-order shear deformation theory to take into account the shear deformations of the adherence, and the adhesive is modeled as a simplified continuum consisting of springs in normal and shear direction, which is often referred to as weak interface. And so this framework leads to two coupled ordinary differential equations with constant coefficients, which can be solved analytically. So with corresponding boundary conditions, so we can obtain the adhesive stresses. For the energy quantities, a very classical approach is used. It is assumed that the released energy of a crack advancement corresponds to the strain energy that is stored in the spring directly ahead of the crack tip, and in this way the differential energy release rates can be given as follows. And then to make the step to obtain the incremental quantities, there we can integrate over the crack length and average over the crack length. So we have the adhesive stresses, we have the incremental energy release rates, so we can apply the coupled criterion, and in a general form it predicts crack onset if both criteria, the stress criterion, as you can see here, and the energy criterion are fulfilled simultaneously. And here F just represents an equivalent stress function with regard to material strength parameters, and on the right the energy criterion, the function G represents the incremental energy release rates with regard to fracture toughnesses on the material. And in this framework, in general, the two-dimensional optimization problem has to be solved, and to find the failure load of an adhesive joint, and the failure load here is defined as the smallest load that satisfies both conditions simultaneously. And since we have in the present case decreasing stresses with respect to the potential locus of failure, and we have increasing energy release rates with respect to the crack length, the whole optimization problem simplifies, and the inequalities revert to equalities. And this optimization problem can be solved very efficiently by deriving an implicit equation for the finite crack length, solving for the finite crack length, and obtain the failure load by inserting the finite crack length in one of the two criteria. And in this sense, this present analytical model is a very efficiently one, we can obtain failure loads of balanced joints at most 1 second. If we have axially loaded single lap joints, we have to take into account the nonlinear dependence of the applied tensile force on the general loading. So it takes around 3 seconds, and for more complex cases with dissimilar terms and different materials, it takes around 3 times longer. So we go one step back to the optimization problem, and we analyze different stress and energy criteria. At first, the stress criteria, the following are observed. The principal stress criterion relating the maximum principal stress to tensile strength, and the more Coulomb-like criterion and the elliptical criterion has been analyzed, and different energy criterion has been analyzed. The first one is a Brittle-like criterion. The second is a linear interaction law of the mode 1 and 2 contributions of the incremental energy release rate. And the last one is an energy criterion assuming a fracture toughness which depends on the mixed mode angle, which has also been used by my teachers, analyzing inclusion in a matrix and debonding and inclusion in a matrix. And at first we looked at steel epoxy steel single lap joints. On the left you can see the failure load with respect to the adhesive thickness, and the dashed lines are the finite crack length. On the left we varied the stress criteria, and you can see that stress criteria have no major influence on the failure load. It's nearly constant for all 3 different stress criteria, but the finite crack length show large deviations. And on the right you can see the influence of the energy criteria. They have an impact on the failure load. The curves are just translated on the y-axis, but have no major impact on the finite crack length. And we made a comprehensive comparison with experimental results and concluded that we have the best results for the linear interaction law of the incremental energy release rates, and we chose the principal stress criterion since we have only the tensile strength as a fracture parameter. So the next results are always with the linear interaction law of the principal stress criterion. And in addition, we introduce a brittleness number, as already has done by Cornetti and Weisgeber and Becker in previous work, and we have seen this on Monday. Takes this form, and if mu equals 1, it corresponds to linear elastic cover to brittle behavior, so we can expect a brittle response of the structure for low brittleness numbers, and an indication of the quantification limit for the application of the carbon stress and energy model as given by Weisgeber and Becker's work. So we made a comprehensive comparison to experimental results. You can see here results from the adhesive single lap joints. You can see that this adhesive thickness effect is captured correctly, which is a nice feature of this finite fracture mechanics approach. You can see the experimental results with respect to the overlap length, which is covered correctly. And additionally, we have found an experimental test series by Goyo et al. They investigated several single lap joints with the Loctite 330 and T-peel joints, and since we hadn't the material data, the fracture parameters, we made and fit to the experimental results of the single lap joints, so we minimized this relative error between experiments and the predictive failure loads, obtained this couple of tensile strength and fracture toughness in mode 1, assumed that the fracture toughness in mode 2 is 2 times the fracture toughness of mode 1, which is a common assumption for structural adhesives, and then we predicted the failure loads of this T-peel joint by taking these 2 as input parameters, and made a very good agreement with the experimental results. And since it is a general approach, we also considered an L joint and some exotic joint configuration, a T-peel joint, and sorry to forget, we also made this cohesive zone model approach to have a validation. Since we had some joint configurations we couldn't find experimental results in literature. As seen also before, the finite fraction mechanics solution is in good agreement with the numerical results. We've seen a good agreement with the experimental results, and it always gives conservative estimates of the failure load. And we always see that the brittleness number is within the interval of the indication limit proposed by Weisberger et al. So it is a very nice tool. And finite fraction mechanics model, an analytical one, has been presented for brittle failure using the carbon stress and energy criterion. The impact of geometric parameters in different stress and energy criterion has been analyzed, and it's a highly efficient analysis model. Good agreements to experience. Thank you for your attention.